Salt is an ionic bond, so sodium chloride has an ionic bond. They are not a molecule. Okay? We're going to find out in a second what they are, but they are not a molecule because a molecule deals with a covalent bond that's sharing of electrons. All right? An ionic bond is where you steal or give away electrons. Big difference, cannot call salt a molecule. Please, please, please don't do that. Okay? But you've got plenty of different examples of that. Like I said though, those electrons may not be shared equally. Well, how do you know if they're going to be shared equally or not? That deals with electronegativity. Okay, whoa, 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 whoa. Nah, don't freak out. Electronegativity is a big fancy schmancy word that basically says who has the strongest pull on electrons. Okay? Now, let's look back at our electron right here. Our atom and what's going on. So, again, nucleus. What's in the nucleus? Your positive protons and your neutral neutrons. You have your electrons on the outside, right? Now, hang on. Between this atom and I'm about to draw you another one. And this atom. Which one of these atoms is going to have a stronger pull on this electron? That atom that has an electron 2 electron shells out, or the one that has the electron 4 electron shells out? Well, where is the pull coming from? What is pulling this electron to the nucleus? Opposites attract. That proton. The protons are pulling on the electrons. So who's going to have a stronger pull? 2 shells out or 4 shells out? 2 shells out, right? So, hang on. So, 2 shells out or 4 shells out? Who's going to have a stronger pull? Which nucleus is going to pull on that stronger? Harder. 2 shells out or 4 shells out? The 2, right? So, as you go up, you're going to have a stronger pull on your electrons. Yes? Okay. Let's go back to the octet rule. If you're in group 1, how many valence electrons do you have? You have 1. How many more do you need? You need 7. Well, let me ask you this. What's easier? Give 1 away or go find 7? You're going to give 1 away, right? If you're in group 17, how many valence electrons do you have? You got 7. How many more do you need? 1. So if you've got 7 valence electrons and you need 1 more, what's easier? Throw 7 away or go find 1? Go find 1. So this guy, anybody here, is going to have a stronger pull on the electronegativity, on the electrons. So as we go this way across the periodic table, you're going to have a stronger pull on your electrons. So as I go up, and as I go to the right, I'm going to have the strongest pull on electrons. So, I want you to understand this and instead of trying to memorize it. So, based on this piece of information, now, hang on. Is group 18 going to have a strong pull on electrons? Is group 18 going to have a strong pull on electrons? 18? Who's got a nice full electron shell? You. They're not going to have any pull. Well, hang on. They're not going to have a pull for the most part because their electron shell's full. So they don't count. So which element out of this entire periodic table has the strongest electronegativity. The higher I go, I get stronger. The furthest to the right I go, I get stronger. So your strongest electronegativity element is fluorine. Yay! What the heck is fluorine? I don't know. Well, I do, but in living things, remember, what were the 4 elements that made up 96% of all living matter? Remember, CHON, carbon, hydrogen, oxygen, nitrogen, CHON. Which one of those 4 is closest to fluorine? Oxygen. So, in most reactions of living things, your most electronegative element is going to be oxygen. You're going to hear that a lot. Okay? So, that's the electronegativity. All right? And I'm about to show you the electronegativity chart. But I need to erase all this. So hopefully you're cool with it. Again, do not try to memorize. Understand. This is not a class about memorization. This is a class about understanding. If you try to memorize the day of the test, you will be crying. Sorry. I can tell who tries to memorize. This is not a memorization class. This is an understanding class. Okay? So, if you have, here we go, electronegativity chart, here we go. So fluorine, perfect 4.0. That is the strongest electronegativity chart. Remember I told you noble gases don't have a pool on electrons? Yeah, sure enough, there's an exception. Remember the whole always and never thing? Yeah, that's why. Right there. Xenon technically has a pool on electrons. Don't ask me why. Let's just leave it alone. We're going to ignore that for a second. Well, for the sake of our class, we're going to go bye-bye. But here's your fluorine. Here's your oxygen. Now, remember, H2O, so 2.1 to 3.5. There is not an even number, equal number between the two. So these two guys are not going to share the electrons equally. They are not even. They're not, stubborn. They're not the same. So those electrons are not being shared equally. That electron is going to spend more time down here in the oxygen. Let's draw it. Remember Mickey Mouse. I like it better. The ears are your hydrogens. The face is your oxygen. Your electron is going to spend more time down here. Your electron has what charge? Negative, slightly negative. The hydrogens are slightly positive. Okay? So, we've got the oxygen down here. Your electron is going to spend slightly more time down here, making the ears, the hydrogens, slightly more positive. Because your oxygen has a 3.5 and your hydrogen has a 2.1. Before you even ask, and before you even think it, you do not need to know this chart by heart. You will not need this chart on the test. This is just to make you visualize what the heck is going on. Okay, so relax. But, fluorine, so we're still sharing electrons, not equally. So it is a covalent bond, but it's polar. Because the electrons are not shared equally. So it's a polar covalent bond. Okay, well what about oxygen? O2, the oxygen we breathe. O2, oxygen to oxygen, 3.5 to 3.5. We're going to be sharing electrons, so it's a covalent bond. 3.5 to 3.5, the electronegativity, the pull on the electrons is the same, so it's a non-polar covalent bond because the electrons are shared equally. Hydrogen, H2, hydrogen gas, same thing. Covalent, the electrons are shared. 2.1 and 2.1, they're shared equally, so that is a non-polar covalent bond. Okay? Salt, sodium chloride. Sodium is 0.9, chlorine is 3.0. That difference between the two is too great. They are not going to share their electrons. Sodium's going to say, take the dang on electron. It is better for me to just give it away and drop to the previous electron shell. And chlorine's like, good, because I have 7, I only need 1 more, so I'm going to steal it from you anyways, so I can have my outer shell full. That is an ionic bond because the electrons are not shared, they are stolen or taken. And it is not a molecule, remember, because if it's a molecule, it has what kind of bonds? Covalent, where we share the electrons. Okay. when sodium gives an electron, he's going to end up with more protons than electrons, right? The electrons he's going to have one less electron, so he's going to have one more proton. So he's going to have a +1 charge. Chlorine, since he had 7 electrons, he needed one more. He took on an extra electron. He has a -1 charge, right? These are ions. Well, depending on if you have a positive or negative charge, you have a different name. You see that right there? Cation. The T looks like a positive charge. So a cation is a positively charged ion, and an anion, you have an extra N, you're negatively charged. That's how I remember it. Cation, positively charged, anion, negatively charged. Okay? That's it. Nice and simple, to the point, move on with life. And just one more time summarize, covalent electrons shared, molecules formed, ionic electrons not shared, ionic compound, also known as a salt, is formed. Okay. Most important large, so we talked about strong bonds. I'll be right back. I gotta get you your DNA molecule. Now we gotta talk about weak bonds. Why in the world would we have the weakest bonds, one of the weakest bonds, holding together one of the most important molecules in an organism? Anybody remember? High school bio? Anybody remember? If not, it's okay. We have to unzip the DNA in order to go ahead and copy it. And then we also have to unzip it in order to make proteins. It's a process called transcription and translation. If you remember that, that's awesome. If you don't worry about it. Okay? So we need the hydrogen bonds that holds the 2 halves of DNA together to be weak so we can unzip it. So we can open it up and make the copies and then transcribe and translate depending on what we're doing. However, the type of bonds that make up the backbone of DNA right here are covalent bonds. Very strong. Because what we don't want is this. We don't want the DNA to break up like that. Okay? Good. Hydrogen bonds. Hydrogen atom covalently bonded to an electronegative atom. So when you have 2 water molecules bonded to each other, that's thanks to hydrogen bonds. You're going to have the hydrogen, the ears, that bond to the oxygen, electronegative atom, right? And when they do that, that's a hydrogen bond. That's what allows oxygen to, water molecules to have such a strong surface tension. So, you've got nice examples right there. Thank you. Okay, almost there. 4 more slides. Van der Waals interactions, ever-changing hotspots of positive and negative charge of atoms. This is what allows your geckos to walk up walls. However, because they are so weak, this is why you will not have a 6 foot long gecko. Okay? It's one of the reasons why geckos can only get so big. I apologize, the cool link has been taken down, but it was just basically showing you this and the positive negative charge ions and interactions going on, and they just took it down. Sorry. So, but there you go. This shows you how, depending on the type of atoms and the type of bonds that they have, and whether they have unshared electrons being bonded with or not, what kind of shape the actual molecules will make. You don't need to know this for our purposes. However, it's important to realize that that will dictate its function. Okay? Finally, chemical reactions. The making and breaking of chemical bonds, which will lead to changes in composition of matter. Whatever you put into a reaction, those are your reactants. Whatever comes out of it are your products. All right. It's your friends or your spouses or your significant others or your child's birthday coming up. And you want to make them a birthday cake. So You take your flour, you take your eggs, you take your butter or your oil, vanilla, mix it all up. Those are all your reactants. And then you put it in the cake pan, put it in the oven. By the way, I just do it a box cake, but whatever. Put it in the oven. It's done. You take it out. You now have your product, a cake, right? Are your reactants still in that cake? Are your eggs, your flour, your, forgot baking soda, your sugar, your vanilla, all that? Yes, it's all in. Great. Can you reach into the cake and pull out the eggs? No. Can you reach in there and pull out the flour? No. Can you get the vanilla out? No. The sugar, the butter or the oil? No. Okay, get my drift. So even though the reactants are still in there, they're in a different format, right? You can no longer find them in the same format, but they're still in there. And that's what's going on with reactions. And we want you to keep that in mind, okay? Whatever you have on this side, you have to have it on the other side. Whatever goes into the reaction has to be on the other side. So if you have 5 carbons that come in, you have to have 5 carbons that come out. They just might be in a different placement, okay? You need to keep that in mind. All right. And then those reactions will keep going until they reach equilibrium. A lot of times those reactions are reversible. One of the biggest ones that we can think of in biology. Can you think of it? Think of plants, think of light, photosynthesis, and then its opposite would be cellular respiration. It's not a true opposite because for photosynthesis, the energy that goes into photosynthesis is light energy, and then for cellular respiration, the energy that comes out of it is chemical energy in the form of 3 little letters, A, T, B. Those are the chapters coming up. All right? Okay, we finished the first chapter, chapter 2, and we'll go on to chapter 3. Thanks so much.